Tonight, the universe has already given us its answer, and the answer is silence. Not the silence of a cosmos still waiting to be filled, but the silence of a cosmos that has already tried for 14 billion years across 2 trillion galaxies and failed to produce anything like us. The great filter is not a wall standing between humanity and the stars. It is something we already crawled through, bleeding and improbable, billions of years before the first human being drew breath. Earth is not a typical world that happened to develop life. It is a miracle so statistically obscene that the honest scientific conclusion, the one most researchers are still too cautious to say plainly, is that we may be alone. Not eventually alone. Not metaphorically alone. Alone right now. In the only way that matters. The sole planet in the observable universe that crossed every barrier, survived every extinction, threaded every needle, and produced a mind capable of looking back at the darkness and wondering why it's so quiet. That question has an answer, and it is not the one that makes good science fiction. For decades, the dominant fear surrounding the Fermi Paradox has been forward-facing. The idea that civilizations like ours are stopped by something ahead, some catastrophic wall of war, disease, or self-destruction that no intelligence survives. That version is frightening and it sells well, but the evidence does not support it as a primary explanation. What the evidence supports, when you stack the geology, the astrophysics, the cellular biology, and the planetary science together into a single unbroken argument, is something far more disorienting. The barrier was never in front of us. It was the road itself, every meter of it. And the road was so treacherous, so riddled with bottlenecks that each required a separate near miracle to survive, that the overwhelming likelihood for any given planet in this universe is not fire, not war, not climate collapse. It is simply never getting started. What we are about to walk through over the next 2 hours is that road, every contingency, every bottleneck, every moment in the 4 billion year history of this planet where the thread nearly broke and didn't. By the time we reach the end, the silence of the sky will no longer feel like a mystery. It will feel like the only possible outcome. And the only remaining question will be the one that has no comfortable answer. If we are truly the universe's single surviving experiment in complexity and consciousness, what exactly does that demand of us? We will get there. But to understand the way to that question, we first have to understand the silence that made it necessary. In 1950, the physicist Enrico Fermi sat down to lunch at Los Alamos National Laboratory with a handful of colleagues and, somewhere between the soup and the main course, asked a question so simple it should not have taken 70 years to still be unanswered. If the universe is as old and as vast as we believe it to be, and if the ingredients for life are as common as they appear, then where's everybody? That was the whole question. For words, where is everybody? His colleagues laughed. The question felt almost naive, the kind of thing a child asks when they first learn that the stars are other suns. But Fermi was not being naive. He was being precise. Because the math underneath that question, when you actually work it out, produces a result that is genuinely, profoundly disturbing. The Milky Way galaxy is approximately 13 billion years old. It contains, by current estimates, somewhere between 200 and 400 billion stars. A substantial fraction of those stars, recent surveys suggest more than half, host at least one rocky planet. The galaxy has therefore had more than 10 billion years to generate habitable worlds, and it appears to have generated them by the billions. If even a vanishingly small fraction of those worlds develop life, and if even a vanishingly small fraction of that life develop technology, the galaxy should by now be saturated, overflowing, with signals, structures, and evidence of intelligence. Radio transmissions spreading outward at the speed of light. Megastructures altering the light curves of stars. Probes arriving in every system, sent by civilizations that had millions of years head start on us. At the speeds achievable even with plausible near-future propulsion, a single sufficiently motivated civilization could colonize the entire Milky Way in somewhere between 1 and 10 million years. 1 million years sounds like an eternity. On a 13 billion year canvas, it is a rounding error. A civilization that arose 10 million years before us, which is nothing cosmically, less than a heartbeat, should have had time to reach every corner of this galaxy, leave unmistakable fingerprints on every star system, and make the question of their existence completely and utterly unanswerable. We should not be asking where they are. We should be surrounded by the evidence of their passage. We are not. The sky is empty. The frequencies are clean. Every Sirius SETI survey conducted over the past 6 decades, monitoring millions of stellar frequencies across decades of observation, has returned nothing that survived scrutiny. The most famous candidate, the WOW signal of 1977, was a single burst, 72 seconds long, that never repeated and was never explained. Everything else has been pulsars, interference, instrument noise, and human error. The silence is not a gap in our data. It is the data, and the silence is, statistically, screaming. This is what scientists call the Fermi Paradox, though paradox is almost too general a word for it. It is not a paradox in a mathematical sense, a logical contradiction that proves a system is broken. It is a paradox in the existential sense, a collision between what the universe should look like and what it actually looks like, with no obvious way to reconcile the two without accepting something deeply uncomfortable about our place in it. The Drake equation was an attempt to give that discomfort a structure. In 1961, the astronomer Frank Drake sat down before the first major SETI conference and wrote a formula on a chalkboard, not because he believed it could produce a precise answer, but because he wanted to identify the places where our ignorance lived. The equation multiplies a chain of probabilities together. The rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life actually arises, the fraction where that life becomes intelligent, the fraction that develops communicable technology, and finally the average lifespan of such a civilization before it goes silent. Multiply all of those together, and you get an estimate of how many communicating civilizations exist in the galaxy right now, at this moment. The problem with the Drake equation is not that it is wrong. The problem is that it is a skeleton. It tells you which bones need flesh, but it does not provide the flesh. When Drake first applied it in 1961, almost every variable except stellar formation rate was complete guess, an educated intuition at best. Optimistic scientists plugged in optimistic numbers and arrived at millions of civilizations. Pessimistic scientists plugged in pessimistic numbers and arrived at one. One meaning us, meaning the galaxy is biologically empty, except for the single species currently arguing about the equation. For most of the last 60 years, the scientific community has implicitly preferred the optimistic reading, because the pessimistic reading carries implications that are genuinely hard to sit with. The optimistic reading says, the universe is teeming with life. We simply haven't found each other yet. It preserves the intuition, widespread and deep in human culture, that life is a natural consequence of chemistry, that wherever the right conditions exist, something will crawl out of chemistry and begin the long journey toward complexity. The pessimistic reading says something else entirely. It says, life is not a natural consequence of chemistry. Or if it is, then something else, some step further along the chain, is so catastrophically improbable that it might as well not exist anywhere but here. That step, or that series of steps, is what the evolutionary biologist Robin Hansen named the Great Filter in 1998. The Great Filter is whatever is responsible for the silence. It is the explanation for why the galaxy looks the way it does. Not teeming with intelligence, but bare and quiet, populated by stars and gas and dust and occasional rock, and nothing that has ever built a radio transmitter. Something is filtering civilizations out. Some barrier exists between simple chemistry and the kind of complex, communicating intelligence that leaves traces in the universe. And the central, agonizing question of the Great Filter is deceptively simple. Are we on the near side of it or the far side? If the filter is ahead of us, if the barrier between where we are and where a true interstellar civilization lives is still waiting to be encountered, then the silence of the sky is a warning. It means that civilizations reach roughly our level of development and then stop. They stop because they destroy themselves with weapons, or with ecological collapse, or with some technology they cannot control. They stop because biology has an upper limit that intelligence cannot transcend. They stop because of something we haven't imagined yet. But they stop universally, reliably. The great silence is, on this reading, a graveyard. Every quiet star is a marker for something that almost made it. This is the version of the Fermi Paradox that gets written about most often, and for understandable reasons. It is urgent. It carries a direct implication for us, right now, in our current civilization, with our current weapons and our current trajectory. If the forward filter is real, we are not merely wondering about alien life. We are reading our own obituary and trying to figure out which paragraph describes how it ends. But the forward filter, for all its narrative power, has a problem. Several problems, in fact. And they become harder to ignore the more carefully you examine the planetary and biological data assembled over the last 30 years. The first problem is this. If civilizations reliably destroy themselves at roughly our stage of development, you would expect to see, scattered across the galaxy, the ruins, the electromagnetic afterglow of a civilization that burned bright, and then collapse will be detectable for millions of years. The structural signatures of megaprojects, Dyson spheres partially constructed, stellar engineering in intermediate stages, should persist even after their builders are gone. Ruins are everywhere on Earth, and we have only been building for a few thousand years. A civilization that burned for 1 million years before collapsing would leave traces that should be visible across thousands of light years. We see none, not one candidate. The sky is not full of ruins. The sky is full of nothing. The second problem is statistical. Even if 99% of civilizations destroy themselves, the remaining 1%, given the age of the galaxy and the number of opportunities, should have colonized the observable universe by now. A filter that is 99% effective is catastrophically insufficient to explain a silence this complete. You need a filter that is not 99% effective. You need a filter that is, for all practical purposes, total. And a filter that total, positioned ahead of us on the timeline, should terrify us in a way that goes beyond policy discussion or scientific curiosity. It should be the single most alarming fact in human history. And yet most people, most scientists, even do not walk around in a state of existential paralysis about the Fermi Paradox. Part of that is denial. Part of it is the difficulty of internalizing numbers this large. But part of it, a growing part, supported by a growing body of observational evidence from planetary science, astrobiology, and astrophysics, is a quiet, unsettling suspicion that the forward filter explanation is simply not the right one, because there is a second interpretation. And it begins not in the future, but 4.5 billion years in the past, with the formation of a planet that should not exist in the form that it does. Earth is not a generic habitable world. It is not the predictable output of common planetary formation processes applied to a common star in a common region of a common galaxy. It is, when you examine the specifics, a nested sequence of improbabilities so tightly interlocked that removing any single one of them collapses the entire structure. Not metaphorically, physically. Remove the moon, and the axial tilt of this planet destabilizes over millions of years, swinging between extremes that make long-term biological complexity impossible. Remove Jupiter from its current orbit, and the impact rate on the early Earth increases by orders of magnitude, enough to sterilize the surface repeatedly before complex life can gain a foothold. Move the Earth 10% closer to the Sun, and you trigger a runaway greenhouse effect that boils the oceans dry within 1 billion years. Move it 5% further out, and the early Sun, which was 30% dimmer than it is today, cannot prevent a global glaciation that locks the planet under ice and never thaws it. Each of those contingencies is real. Each of them is supported by current planetary science. And each of them, individually, might be survivable, might be the kind of constraint that a sufficiently common type of planet can satisfy by pure statistical frequency. The devastating realization is that they are not individual constraints. They are simultaneous constraints. Earth satisfies all of them concurrently, across a timeline of 4 billion years. The probability of that is not a percentage. It is a fraction so small that it approaches, from the wrong direction, something that sounds less like an equation and more like a verdict. The backward-facing great filter is the hypothesis that this is the explanation. Not that civilizations arise and are then destroyed, but that civilizations almost never rise in the first place, because the road complex life is lined with barriers so severe that the vast majority of potentially habitable worlds never make it past the first few. Life may be common in the simplest sense: microbial, single-celled, ancient, and permanently stuck. Intelligence may be not merely rare, but singular. And if that is true, then the silence of the sky is not a warning about where we are going. It is a description of where everything else stopped. This is a possibility we're going to take seriously for the next 2 hours, not because it is the most comforting possibility, and not because the science is fully settled, but because it is a hypothesis that the converging evidence from a dozen separate scientific disciplines is quietly and consistently pointing toward. The data from exoplanet surveys, from the geology of early Earth, from the molecular biology of the first cells, from the fossil record, from the astrophysics of stellar habitable zones. None of it was collected to prove the rare Earth hypothesis. Most of it was collected for entirely unrelated reasons. And yet, piece by piece, it assembles into the same picture: a universe that is very good at making stars, reasonably good at making planets, occasionally capable of placing a rocky planet in a liquid water orbit around a stable star, and almost completely incapable of crossing the distance between a warm, wet rock and a mind that can look up at the night sky and feel the weight of being the only one. We're going to walk that distance now. Every millimeter of it, every contingency, every near miss and narrow escape. And by the time we are done, the silence will make perfect sense. It will not be comfortable, but it will make sense. And we begin where all of it began, not with life, but with the address. Because before anything could live on this planet had to exist in exactly the right place, not just in the solar system, but in the galaxy itself. And the galaxy, as it turns out, is not hospitable. It is vast and mostly lethal, and the small region within it where complex life is even theoretically possible is narrower than almost anyone imagined before we started measuring it. The galaxy has a habitable zone, just as stars do, and understanding why Earth sits inside it and why almost everything else does not is where the real story of our improbability begins. Picture the Milky Way from above, not the romanticized version, the swirling, luminous pinwheel of 1,000 science documentaries, but the honest version, a structure roughly 100,000 light years across, containing several hundred billion stars, organized into a dense central bulge surrounded by a flattened disk of spiral arms. It is by any measure a staggeringly large object, and it is, by any honest biological accounting, almost entirely uninhabitable. The central region, the inner 10,000 light years surrounding the galactic core, is a killing ground. The density of stars there is so extreme that supernovae, the catastrophic deaths of massive stars, occur at a rate orders of magnitude higher than in the outer disk. A supernova within 30 light years of Earth would be sufficient to strip away a significant fraction of our ozone layer, exposing the surface to ultraviolet radiation at levels lethal to complex biology. Within 10 light years, it would be an extinction event of the first order. In the galactic center, where stellar density is thousands of times higher than our neighborhood, the average distance between stars shrinks to the point where a habitable world would experience sterilizing radiation events not once every 100 million years, but potentially once every few million. Far too frequently for the long, slow accumulation of biological complexity to ever stabilize. Additionally, the galactic center hosts Sagittarius A*, a supermassive black hole 4 million times the mass of our sun, periodically erupting in blasts of X-ray and gamma radiation that propagate outward across thousands of light years. The inner galaxy is not merely hostile. It is, for the purposes of complex life, a closed door. Now move outward, travel past the habitable middle ground, past the quiet suburban spiral arms, and into the galaxy's outer disk, the sparse, dim regions far from the center. Here the violence diminishes. Supernovae become rare. The radiation environment grows gentler. But a different problem emerges, one that operates not through destruction but through poverty. Stars in the outer galaxy formed early, when the universe was young, and the only elements in abundance were hydrogen and helium, the primordial outputs of the Big Bang. The heavier elements, iron, silicon, magnesium, carbon, oxygen in its rocky mineral forms, are manufactured inside stars and dispersed by supernovae. They accumulate over time, generation after generation of stellar life and death, gradually enriching the interstellar medium with the raw materials needed to build rocky planets. In the outer galaxy, that enrichment process never reached sufficient density. The stars are metal poor, and the planets that form around them are gas-dominated, lacking the iron cores and silicate mantles that make worlds like Earth geologically active, magnetically shielded, and chemically complex. You cannot build a living planet from hydrogen and helium. You need the entire periodic table, forged across billions of years of stellar nucleosynthesis, concentrated in a region of space where enough generations of stars have lived and died to scatter those elements in sufficient quantity. Earth occupies neither of those extremes. It sits in a band, roughly 25,000 to 35,000 light years from the galactic center, that planetary scientists and astrobiologists call the galactic habitable zone. This band is far enough from the core to escape the worst of the radiation and supernova density. It is close enough to the center to have been enriched over billions of years of stellar cycling, with the heavy elements necessary for rocky planet formation. It is relative to the full diameter of the Milky Way, a narrow ring, and within that ring, Earth has orbited stably in a nearly circular path for 4.5 billion years, a path that has kept it clear of the dense, dangerous spiral arms that periodically sweep through the galactic disk like slow-moving waves of stellar violence. A more elliptical orbit, one that plunged regularly through those arms, would expose the solar system to enhanced radiation and gravitational perturbation on a cyclical basis. The stability of Earth's galactic orbit is itself a contingency. It is one of the outermost layers of protection system that most planets never possess in full. But even a perfect galactic address means nothing without the right star at its center. And the Sun, examined honestly, is a profoundly unusual object, not in the sense of being exotic or unprecedented, but in the sense of being calibrated across every relevant parameter to a degree of stability that is exceedingly rare among the stellar population. The most common stars in the Milky Way are not stars like our Sun. They are M-dwarf stars, red dwarfs, small, dim, cool objects that make up approximately 75% of all stars in the galaxy. They are long-lived. They are numerous. And for a time, they seem like promising hosts for habitable worlds, precisely because their abundance means there are billions of potentially habitable planets in their systems, and their extraordinary lifespans, some will burn for trillions of years, provide enormous windows for life to develop. But the picture that has emerged from the last 2 decades of observational data is not encouraging. M-dwarf stars are magnetically violent in ways that their small size and cool temperatures conceal. They produce stellar flares, eruptions of X-ray and ultraviolet radiation from their surfaces, at frequencies and intensities that dwarf anything our Sun generates. And because habitable zone planets around M-dwarfs must orbit extremely close to their star to receive sufficient warmth, far closer than Mercury's orbit around the Sun, those planets are subjected to this radiation bombardment at point-blank range. Detailed atmospheric modeling, supported by direct observation of nearby M-dwarf systems, suggests that the sustained flare activity would erode a planet's atmosphere over geological timescales, stripping away the very gases that create pressure, warmth, and the chemical environment necessary for biology. The planets of M-dwarfs may be waterless, airless, radiation-scorched rocks. The most common stars in the galaxy may, in fact, be the least capable of nurturing complex life. Our Sun belongs to a class, G-type main sequence stars, that represents roughly 7% of the stellar population. It burns with a steady, relatively benign output that has remained within a narrow range of luminosity for billions of years. It produces solar flares, but at intensities and frequencies that the Earth's magnetic field and atmosphere can absorb without biological catastrophe. It exists at a mass that balances two critical opposing pressures. It is large enough to have formed quickly, seeding the solar system with the heavy elements needed for rocky planets, but not so large that it burns through its hydrogen supply in a few 100 million years before complex life can arise. Massive stars live fast and die violently. The Sun's modest mass gives it a lifespan of roughly 10 billion years. It is currently halfway through that span, providing an enormous temporal window that a gradual, grinding process of biological evolution requires. There is something almost suspicious about the way these parameters align. Not so large as to burn out too soon. Not so small as to irradiate everything nearby. Not so magnetically active as to strip atmospheres. Stable enough, warm enough, long-lived enough, positioned precisely where the heavy elements are rich enough. All at once. The Sun is not a miracle in the theological sense, but it is a profound outlier in the statistical sense, and the distinction between those two things, out here in the data, begins to blur. Even with the right star at the right galactic address, Earth still needed one more improbable event to become the world it is, an event so catastrophic in its scale and so constructive in its consequence that it reads less like planetary formation and more like an accident that turned out to be the most important accident in the history of the solar system. Approximately 4.5 billion years ago, the young Earth, still geologically raw, still largely molten, still accumulating mass from the debris of solar system formation, was struck by a Mars-sized body. The name given to this hypothetical impactor is Theia, after the Titan in Greek mythology, who was the mother of the moon. The collision was not a gentle nudge. It was a planetary-scale catastrophe, an impact so energetic that both objects were partially vaporized, their materials mixing and ejecting into orbit as a vast ring of molten rock and vapor. Over the course of thousands to millions of years, that debris ring coalesced under its own gravity into a single large body, the Moon. The Moon is, by every comparative standard we have, absurdly large for a satellite of a rocky inner planet. Its diameter is more than a quarter of Earth's. Its mass is more than 1% of Earth's. No other rocky planet in the inner solar system has anything remotely comparable. Mars has 2 tiny captured asteroids. Mercury and Venus have nothing. The existence of a satellite this large, this close, is not a generic output of planetary formation. It required a very specific collision at a very specific angle and velocity between 2 bodies of very specific masses at a very specific time in the solar system's history. Remove any of those parameters and you either get no moon at all, or you get a debris field that never coalesces into a single massive body. The improbability of the moon's existence is not a philosophical claim. It is a consequence of orbital mechanics and impact physics, and planetary scientists take it seriously. But the moon's improbability would be an interesting footnote, and nothing more if the moon did not do something extraordinary for the planet below it. It does. The moon acts as a gravitational anchor for Earth's axial tilt, the angle at which our planet's rotational axis leans relative to the plane of its orbit around the sun. That tilt is currently 23.5 degrees, and it is responsible for the existence of seasons. But the critical word is not the tilt itself. The critical word is stable. Earth's axial tilt oscillates slightly over long cycles, between roughly 22 and 25 degrees, but remains within that narrow range across hundreds of millions of years. The moon's gravitational influence is what enforces that stability, damping down the gravitational perturbations that the other planets, primarily Jupiter and Saturn, exert on Earth's rotational dynamics. Without the moon, the story changes completely. Simulations of a moonless Earth consistently produce an axial tilt that would swing, over tens of millions of years, between nearly 0 degrees and as high as 85 degrees. 0 degrees means no seasons at all, permanent equatorial heat, permanent polar cold, with winds so extreme that the temperature differential between regions would drive atmospheric circulation patterns that no complex terrestrial ecosystem could withstand. 85 degrees of tilt means the poles would periodically face the sun directly, melting any polar ice and flooding coastlines. while the opposite hemisphere freezes into permanent winter darkness. These swings would be cyclical and relentless, with no stabilizing force to hold the climate in the moderate, predictable range that complex land-based biology requires. The great sweep of evolutionary history on Earth, the colonization of land, the development of forests, the diversification of animal body plans, all of it happened within a climate regime stable enough to permit slow, generational adaptation. That stability was not free. It was purchased by the improbable catastrophe of the Theia impact 4.5 billion years ago. And yet, even with the right star, the right galactic neighborhood, and the right moon, Earth faced a bombardment problem. The early solar system was not the orderly, well-spaced arrangement of planets we inhabit today. It was a chaotic, crowded environment filled with leftover debris, asteroids, comets, and planetesimals that had not been swept into the planets during formation. That debris represented an existential threat to any world attempting to develop stable biology, because frequent large impacts reset the surface. They vaporize oceans, sterilize crusts, and push developing ecosystems back to zero repeatedly. The window of opportunity for life to gain a foothold is narrow enough without having that window repeatedly shattered. Jupiter solved this problem, not by design but by physics. Jupiter is 11 times the diameter of Earth and more than 300 times its mass. It is, by a significant margin, the largest planet in the solar system, and its gravitational influence extends across an enormous volume of space. Asteroids and comets that wander into the inner solar system on trajectories that might otherwise intersect with Earth frequently encounter Jupiter first. Some are captured into orbit around Jupiter. Some are flung onto hyperbolic trajectories that eject them from the solar system entirely. Some are drawn in and swallowed by the gas giant's atmosphere. The Shoemaker-Levy 9 impact of 1994, when a fragmented comet smashed into Jupiter in a sequence of strikes that would have been globally catastrophic if they had hit Earth, provided modern observational evidence of a process that has been ongoing for billions of years. The precise degree of Jupiter's protective influence is still debated among planetary scientists. Some models suggest it is more complicated than a simple shield, that Jupiter's gravity can also perturb asteroid orbits inward rather than outward, increasing impact probability under certain conditions. But the broad consensus remains that the presence of a gas giant in the outer solar system significantly reduces the long-term bombardment rate experienced by the inner planets, and that Earth has benefited from this reduction across the full span of its biological history. Without Jupiter at its current mass and orbital position, the impact rate on early Earth would have been dramatically higher, the sterilization events more frequent, and the narrow window of climatic stability required for complex evolutionary processes far less likely to have persisted long enough to matter. What we have now is a solar system that looks, in retrospect, almost architecturally designed for protection of one specific inner planet, a massive outer guardian deflecting the debris, a large satellite anchoring the climate, a stable, gentle star providing consistent energy, a privileged position in a quiet ring of the galaxy, far from the sterilizing violence of the core. These are not separate features. They are interdependent layers of a single protection system, and they all had to be in place simultaneously, maintained across billions of years, for the next stage of the story to be possible. But protection from the outside, as it turns out, is only half the equation, because Earth also had to protect itself from the inside, from the chemical and atmospheric instabilities that, on most rocky worlds, eventually collapse the conditions for liquid water and breathable air into something uninhabitable. And the mechanism Earth uses for that internal regulation is one that most rocky planets appear to lack entirely. Beneath your feet, right now, the surface of this planet is moving, not quickly. The fastest tectonic plates travel at roughly the speed a human fingernail grows, but continuously, over time scales so vast that continents drift thousands of kilometers across the globe in 100 million years. Mountain ranges rise and are eroded flat, and ocean floors are created at spreading ridges and consumed at subduction zones in a slow, grinding cycle that has been running for most of Earth's history. This is plate tectonics, and it is not merely a geological curiosity. It is the reason this planet's atmosphere has remained breathable. It is the reason Earth is not frozen solid, or boiled away, or been swallowed by its own greenhouse gases the way Venus was. Plate tectonics is Earth's thermostat, and most rocky planets in the universe appear to have no thermostat at all. The mechanism is a carbonate-silicate cycle, a long-term chemical feedback loop that regulates atmospheric carbon dioxide over millions of years. When carbon dioxide levels in the atmosphere rise, the planet warms. Warmer temperatures accelerate the weathering of silicate rocks at the surface, a chemical reaction that pulls carbon dioxide out of the atmosphere and converts it into carbonate minerals. Those minerals are eventually carried by tectonic plates into subduction zones, dragged deep into mantle, and cooked at high temperatures, releasing the carbon dioxide back into the atmosphere through volcanic activity. The cycle is slow. It operates on timescales of hundreds of thousands to millions of years. But it is self-correcting. Too much CO2 and the planet warms. Weathering accelerates and the gas is drawn down. Too little CO2 and the planet cools. Weathering slows, and volcanic outgassing replenishes the atmosphere. Plate tectonics is the engine that drives this cycle. Without active subduction, without the constant recycling of surface material into the mantle and back, the cycle stops. Most rocky planets appear to be what geologists call stagnant lid worlds. Planets whose crust is solidified into a single unbroken shell, with no plate tectonics, no subduction, no carbonate-silicate cycle, and therefore no long-term atmospheric regulation. Mars is a stagnant lid world. Venus, despite being nearly Earth's twin in size and composition, is a stagnant lid world. And Venus, as a result, has undergone a runaway greenhouse event that has raised its surface temperature to 460 degrees Celsius and crushed its atmosphere to a pressure 90 times that of Earth's. Venus is what Earth looks like without the thermostat. It is what happens when the feedback loop that keeps carbon dioxide in check fails, and the system finds a new equilibrium at temperatures that melt lead. Why Earth developed plate tectonics and most other rocky planets did not is still an active area of research. The leading hypotheses involve the specific viscosity of Earth's mantle, itself a function of its water content, its thermal history, and its composition, combined with the particular way the early Earth cooled following the Theia impact. These are not simple or easily replicable conditions. They represent yet another layer in the nested structure of contingencies that separates this world from the overwhelming majority of rocky planets in the observable universe. Every layer you add to this structure multiplies the improbability. A planet in the galactic habitable zone, orbiting a stable, long-lived G-type star, with an anomalously large moon, product of a precisely calibrated ancient collision, protected by a massive outer gas giant at the right orbital position, geologically active with functioning plate tectonics, providing billions of years of atmospheric stability. Each of these factors has a probability attached to it, not zero, but not generous either, and because they are not independent, because each one is contingent on a specific chain of prior events that themselves required favorable conditions, the combined probability does not merely add the individual improbabilities. It multiplies them. It stacks them. It produces a number that, when you eventually write it down, looks less like a scientific estimate and more like a philosophical statement about the nature of miracles. And we have not yet arrived at the hardest part. We have not yet crossed the threshold from the physical to the biological. We have not yet asked what happened on the surface of this carefully prepared, improbably positioned, fortuitously protected world. What chemistry had to occur and how improbable it had to occur, and over what enormous span of patient, grinding time, before the first thing that could reasonably be called alive managed to exist. Because the architecture of the miracle does not stop with the planet. It continues down through the oceans, through the chemistry, through the molecular machinery of the cell, all the way to a transition so unlikely, so poorly understood even now, that the scientists who study it most carefully are the ones most reluctant to estimate how often it happens elsewhere. And yet before we descend into that chemistry, before we follow the thread of improbability all the way down to the molecular level, we need to step back and look at the solar system as a whole one more time. Because there is a dimension of Earth protection that operates not on the scale of billions of years, but on the scale of the entire architecture of this planetary system, a dimension that becomes urgently, practically relevant the moment humanity begins to expand beyond this world. And that dimension is geometry. The solar system is not merely a collection of planets orbiting a star. It is a gravitational landscape, a terrain of invisible forces, competing pulls, resonances, and equilibria, regions of stability and regions of chaos. And that landscape has a structure as real and as consequential as any physical geography. To move through it, to inhabit it, to conduct industry or warfare or civilization within it, you have to understand its topology. You have to know where the high ground is. And the high ground in a gravitational landscape is nothing like what intuition suggests. Begin with the asteroid belt, because the asteroid belt is the first place most people imagine when they think about the resources of the outer solar system. And it is the first place where the gap between imagination and reality opens into something vertiginous. Science fiction has given the asteroid belt a specific visual vocabulary. It is a crowded rock field that spacecraft must navigate with reflexes and luck, dodging boulders that fill the frame in every direction, a churning river of stone and metal suspended between Mars and Jupiter. This image is so deeply embedded in popular culture that most people who know intellectually that it is wrong still carry it somewhere in their intuitions. The reality is so different that it requires a specific act of cognitive recalibration to absorb properly. The asteroid belt contains somewhere between 1 and 2 million objects larger than 1 kilometer in diameter. It contains hundreds of millions of smaller fragments. The total mass of all of them combined is less than 4% of the mass of the Moon, spread across an annular volume of space so enormous that the average distance between any two asteroids larger than a kilometer is approximately 1 million kilometers. 1 million kilometers. To put that in a human frame, the distance from Earth to the Moon is roughly 384,000 kilometers. The average gap between individual asteroids in the belt is more than 2.5 times the Earth-Moon distance. You could travel through the asteroid belt in a straight line at random and have a vanishingly small probability of coming within visual range of a single object. The New Horizons spacecraft, the Galileo spacecraft, and multiple other missions have passed directly through the asteroid belt without any evasive maneuvering at all. The crowded rock field is a fiction. The real asteroid belt is an ocean of void, in which isolated objects drift in a silence so complete that most of them have never come within 1 million kilometers of another object in their entire history. This is reassuring in one sense. Navigating the belt is not the obstacle course of popular imagination, but it introduces a different problem, one that becomes acutely relevant the moment human beings begin to mine those asteroids at industrial scale. And that problem is not scarcity. It is a terrifying abundance of kinetic energy stored in objects that, left undisturbed, are harmless, but which, once moved, once nudged from their stable orbital paths by industrial extraction operations or weapon systems or simple miscalculation, become something else entirely. An asteroid 1 kilometer in diameter, composed of nickel iron at average density, has a mass of approximately 2 billion tons. At orbital velocities in the belt, roughly 17 to 25 kilometers per second relative to the Sun, the kinetic energy stored in that object is equivalent to several times the total nuclear arsenal of every nation on Earth combined. Moving it is not difficult. In principle, a sufficiently patient propulsion system, a mass driver, an ion engine, a gravity tractor operating over years or decades can alter trajectory by a fraction of a degree. Over the vast distances of the inner solar system, a fraction of a degree is enough to move an impact point from empty ocean to a major population center. The asteroid does not need to be aimed. It needs only to be released from stability and allowed to fall inward under gravity, and the solar system geometry will do the rest. This is the asteroid belt's true strategic significance, not the metals it contains, though those are staggering in their economic value, but the gravitational leverage it represents. Every mining operation in the belt is, from a certain engineering perspective, indistinguishable in its mechanics from the first stage of a kinetic bombardment system. The difference lies entirely in intent and oversight, and in the outer solar system, Oversight is a function of communication, and communication is a function of the speed of light, which is both finite and, at these distances, punishingly slow. We will return to that problem. But first we need to understand the geometry that makes the belt in the outer solar system so strategically consequential. In 1772, the French-Italian mathematician Joseph Louis Lagrange solved a restricted version of the three-body gravitational problem. The question of where a small object can be placed relative to two large orbiting masses, such that the gravitational forces and the centrifugal effects of the rotating system combine to hold it in a stable equilibrium. His solution produced 5 such points, now called Lagrange points, and their geometry is one of the most consequential facts in the physics of space habitation and space conflict. 3 of the 5 Lagrange points, L1, L2, and L3, lie along the line connecting the two primary masses, and they are only weakly stable. An object placed at L1, L2, or L3 will remain there only if actively maintained. Any perturbation will cause it to drift away over time, requiring fuel expenditure to correct. These points are useful for specific scientific and operational purposes. L2, for example, is where the James Webb Space Telescope orbits, positioned in the gravitational and thermal shadow of Earth, but they are not the points that matter most for long-term habitation and strategic control. L4 and L5 are different in kind, not merely in degree. They lie not on the line between the two primary masses, but at the apex of equilateral triangles formed with that line as the base, 60 degrees ahead of and 60 degrees behind the smaller of the two bodies in its orbit. For the Earth-Sun system, L4 and L5 lie in Earth's orbital path, 60 degrees ahead and behind our planet, drifting in the same orbit at the same orbital velocity, maintaining their geometric relationship to Earth and the Sun as long as the system persists. And they are, unlike the other 3 Lagrange points, genuinely, robustly stable. An object placed at L4 or L5 that is slightly perturbed does not drift away. It oscillates slowly around the equilibrium point in a kidney-shaped path called a tadpole orbit, and will continue to do so indefinitely without any fuel expenditure. They are gravitational wells, shallow ones, but real ones, in which material naturally accumulates. The Trojan asteroids of Jupiter, more than 10,000 known objects, have been sitting at Jupiter's L4 and L5 points for billions of years, held there by nothing but geometry. The strategic implications of this stability are profound and almost completely absent from current political and legal discourse, which is itself a fact worth sitting with. An installation at Earth-Sun L4 or L5 requires no fuel budget for station keeping. It maintains its position relative to Earth and the Sun permanently, without any active support, as long as it physically persists. It has a permanent, unobstructed view of both Earth and the Sun. It cannot be reached quickly from Earth's surface. The journey requires delta-V budget and weeks of transit time, which means any military action against it requires substantial preparation that cannot be easily concealed, and it sits outside the jurisdiction of every existing treaty, in a legal vacuum so complete that no nation or international body currently has any agreed framework for claiming, defending, or contesting it. The Outer Space Treaty of 1967, the foundational document of international space law, prohibits the placement of weapons of mass destruction in orbit or on celestial bodies. It does not prohibit conventional military installations. It does not clearly define what constitutes a weapon system versus a defensive installation versus a commercial facility with defensive capabilities. It says nothing specific about Lagrange points, because in 1967 no nation had the capability to place anything a Lagrange point, and the drafters of the treaty did not consider it a near-term concern. That oversight is now a structural vulnerability in the architecture of international space governance, a gap wide enough to position an entire orbital industrial platform through, with no existing legal mechanism to prevent it. The nation or corporation or coalition that establishes a permanent, fortified presence at Earth-Sun L4 or L5 first will occupy a position of gravitational and strategic advantage that is, in the most literal physical sense, permanent. They will be able to monitor the entire Earth-facing hemisphere of space. They will be able to position assets for rapid deployment to a range of orbital altitudes. They will be difficult to dislodge, Any attacking force must expend fuel and time to climb to the Lagrange point's location, arriving after a journey long enough to be detected and prepared for, while the defenders expend no fuel merely to stay. It is, in the language of military geography, the high ground, but high ground that doesn't erode, doesn't require resupply to maintain, and doesn't exist anywhere in current international law as sovereign or protected territory. Move outward from Earth's Lagrange points to Jupiter's, and the scale of the strategic environment changes completely. Not gradually, but in a qualitative jump that restructures every intuition about command, communication, and control. Jupiter's L4 and L5 points are already occupied, not by human installations, but by the Trojan asteroids, as noted, and studying them has been the purpose of NASA's Lucy mission launched in 2021. But the points themselves in Jupiter's moons represent something different in the context of human expansion, a military and industrial environment so far from Earth that the most basic assumptions of command authority simply do not hold. At Jupiter's average orbital distance of approximately 778 million kilometers from the Sun, the one-way communication delay between Earth and Jupiter ranges from 32 minutes at closest approach to 52 minutes at greatest separation. That is not a nuisance. That is not a scheduling inconvenience. That is a fundamental restructuring of the relationship between a distant outpost and its home authority. Consider what a 35 to 52-minute one-way delay means in practice. A distress signal sent from a facility in Jupiter's system is more than half an hour old before it arrives at Earth. Earth's response, assuming it is immediate, assuming no deliberation is required, assuming the necessary resources are already positioned and ready to move, cannot arrive at the Jupiter system for another 35 to 52 minutes after that. The minimum round-trip communication time is over an hour. In most realistic scenarios, where deliberation, authorization, assembly or response, and transit time are factored in, the gap between an event occurring in Jupiter's system and any Earth-based authority having the ability to influence it is measured not in hours, but in days to weeks. An entire military engagement, the seizure of an orbital installation, the destruction of a mining facility, the blockade and surrender of a colony, can begin, escalate through every stage, and reach a conclusion before the first distress signal has completed its one-way journey to Earth. Not in a theoretical edge case, but routinely as a mathematical consequence of the speed of light and the orbital mechanics of the solar system. Earth's political authority over Jupiter's system is not merely weakened by distance. It is severed by physics. Whatever happens there, and the only entity with the ability to respond in real time is whatever entity is already present. This is the sovereignty debt that the speed of light imposes, and it applies not only to military conflict, but to every dimension of governance. Labor disputes in a Europan mining colony cannot be arbitrated by an Earth-based court operating in real time. Emergency decisions about resource allocation, life support, structural integrity cannot wait an hour for a round-trip consultation. The medical, engineering, legal, and political decisions of a Jupiter system installation must be made by the people in the Jupiter system, using the judgment and the authority they carry with them, because no other authority can reach them in time to matter. The colonies of the outer solar system are not merely distant. They are, in the operational sense that governance requires, independent, whether or not any political document acknowledges it. The moons of Jupiter add a further layer to this isolation, because they are not merely far. They are, by any biological standard, hostile in ways that make the vacuum of open space seem almost welcoming by comparison. Jupiter is the largest planet in the solar system, and its mass, more than twice the combined mass of all other planets, generate a magnetic field of proportionate ferocity. The Jovian magnetosphere is the largest structure in the solar system after the heliosphere itself, extending outward from Jupiter by millions of kilometers in every direction. Within that magnetosphere, trapped charged particles, electrons and protons accelerated to high energies by Jupiter's rotating magnetic field, form radiation belts of extraordinary intensity. The inner radiation belt, in which Jupiter's innermost large moons and any human installation in low Jovian orbit would be immersed, delivers radiation doses that will be lethal to an unshielded human being in a matter of hours. Not days, hours. The electronics of the Galileo spacecraft, despite radiation hardening specifically designed for the Jovian environment, accumulated significant damage over its years of operation in the system. Every circuit board, every sensor, every computational system operating in close proximity to Jupiter requires shielding mass that is enormously expensive to lift from Earth's surface and must be maintained against the constant degradation of the radiation environment. Io, the innermost of the 4 Galilean moons, exists in the worst of this radiation environment and adds its own particular horror to the picture. It is the most volcanically active body in the solar system, more volcanically active than Earth by a factor that makes a comparison almost absurd. The tidal forces exerted by Jupiter's gravity, combined with the gravitational influences of the other Galilean moons, flex Io's interior continuously and ferociously, generating heat on a scale that has maintained hundreds of active volcanic systems across the moon's entire surface for billions of years. Lava lakes, sulfur dioxide plumes reaching hundreds of kilometers in altitude, volcanic calderas dozens of kilometers across. Io is a world that is being continuously torn apart from the inside and simultaneously cooked from the outside by Jupiter's radiation. It is as a site for human habitation, essentially a thought experiment in extremity. The sulfur compounds that blanket its surface are toxic. The radiation environment at its orbital distance from Jupiter delivers doses an order of magnitude above the threshold of immediate biological danger. The seismic and volcanic activity makes any fixed surface installation a short-term commitment at best. And yet Io's tidal heating mechanism, the physics of gravitational flexing generating internal warmth, is precisely the same mechanism that makes one of its sister moons the most compelling candidate for extraterrestrial life in the solar system. Europa is the second Galilean moon outward from Jupiter, and it is, under the right framing, either the most hopeful or the most claustrophobically terrifying world in the solar system, depending on which aspect of its reality you choose to emphasize. Beneath the surface of cracked and refrozen water ice, a shell estimated at 15 to 25 kilometers thick, though the uncertainty in that estimate is significant, Europa is believed to harbor a global liquid water ocean. The evidence for this ocean is compelling. The surface geology shows features consistent with a mobile ice shelf floating on a fluid layer. The moon's induced magnetic field suggests a conductive fluid beneath the surface, and the same tidal heating mechanism that tortures Io provides sufficient warmth to maintain liquid water in the interior despite Europa's position far beyond the conventional habitable zone of the Sun. The ocean beneath Europa's ice may contain more liquid water than all of Earth's oceans combined. It has been in contact with a rocky seafloor for potentially billions of years, in a chemical environment where hydrothermal activity, driven by tidal heating, may provide energy gradients sufficient to support microbial life. The scientific case for life in Europa's ocean is not certain, but it is serious, and it is taken seriously by serious people. NASA's Europa Clipper mission, launched in 2024 and currently en route to the Jovian system, will study the moon's ice shell, ocean depth, and chemical composition in detail that no previous mission has achieved. But the prospect of human habitation on or within Europa is an exercise in confronting a layered series of challenges that each, individually, would represent a major engineering achievement, and which together constitute something close to the outer limit of foreseeable human capability. The ice shell must be penetrated, 15 to 25 kilometers of ice, in a radiation environment that degrades equipment continuously, in a gravitational field that makes resupply from Earth a months-long and enormously expensive undertaking. Any installation beneath the ice is cut off from direct communication with space above. Radio signals do not propagate through kilometers of ice with any reliability, meaning that a sub-ice habitat is not merely isolated from Earth by the 52-minute speed of light delay, but isolated from the surface of Europa itself by the physical barrier of the shell. Communication requires relay systems threaded through the ice, maintained against the constant dynamics of a mobile ice shell, In an environment with a tidal flexing that keeps the ocean liquid, also periodically recluses crevasses, shifts the ice structure, and creates pressures that no surface drill convoy can be guaranteed to survive indefinitely. A human habitat in Europa's ocean is not a colony in any sense that the history of terrestrial colonization would recognize. It is a submarine installation in a lightless ocean under kilometers of ice, on a moon immersed in lethal radiation, orbiting a gas giant that is more than 40 minutes of signal propagation from Earth, on a moon where the surface temperature is negative 160 degrees Celsius, and the radiation flux at the surface is enough to kill an unshielded human in a day. The people living there would be, in the most operationally meaningful sense of the word, alone, not lonely in the emotional register, though that too, but alone in the sense that their survival, their governance, their response to emergencies, their relationship to every system that keeps them alive will be a function of their own judgment and their own resources, mediated by no external authority capable of reaching them in time to matter. This is not a failure of political will or legal imagination. It is a consequence of physics. The speed of light is not a policy variable. The radiation belts of Jupiter are not a diplomatic concern. The thickness of Europa's ice is not subject to negotiation. The outer solar system imposes its conditions on human presence with an indifference so complete that describing it as hostility would be a misuse of the word. Hostility implies intent, and the outer solar system has none. It simply is what it is, governed by forces that were in place billions of years before the first terrestrial organism drew energy from a chemical gradient, and which will persist billions of years after the last one ceases to do so. And this is where the geometry of the solar system and the biology of Earth and the silence of the cosmos outside it converge on a single point of extraordinary tension, because the outer solar system, with its radiation belts and its ice-covered oceans and its communication delays that sever the cord of political authority, is not merely a hostile environment for human expansion. It is a mirror. It reflects back at us, in the language of physics and orbital mechanics and electromagnetic spectrum propagation, the same fundamental truth that the planetary science of Earth has been assembling piece by piece, that the conditions for life, for complexity, for civilization, are not generic. They are specific. They are contingent. They are the product of a nested series of favorable coincidences that the universe produces with extraordinary reluctance. The asteroid belt is vast and nearly empty, and the resources it contains are simultaneously staggering in their economic value and terrifying in their kinetic potential. The Lagrange points are gravitational gifts, eternal, fuel-free, strategically decisive, sitting in a legal vacuum that no existing international framework has the architecture to govern. The moons of Jupiter are worlds of extraordinary scientific interest and near prohibitive human hostility, separated from Earth by a communication delay that dissolves the coherence of any command structure attempting to span it. And Jupiter itself, the gas giant that has spent 4.5 billion years as Earth's gravitational guardian, deflecting and absorbing the debris that might otherwise have reset this planet's biology repeatedly, is, at the scale of human expansion, a source of the most ferocious radiation environment in the solar system. The same force that protected Earth from the outside is lethal at close range. The same moon that might harbor life in its buried ocean is encased in ice so thick that reaching that ocean is among the most challenging engineering problems our species has ever attempted to define. The solar system gives and takes in the same gesture, with the same physics, as if the universe had decided that the reward for surviving the great filter is access to an environment that tests at every scale whether survival was deserved. And perhaps that is the most honest framing of where we are in this story. The biological miracle of Earth, every contingency, every narrow escape, every cascading coincidence from the galactic habitable zone down to the molecular machinery of the first living cell, produce one thing above all others: a species capable of looking outward, capable of measuring the silence, calculating the improbability, mapping the geometry of the solar system, and beginning, however tentatively, to move through it. The question of whether that outward movement will be coherent, governed, and survivable, or whether it will replicate in the solar system the competitive, fractured dynamics that have characterized human history on the surface of one small world. That question is not answered by physics. Physics only sets the constraints. The answers come from somewhere else entirely, from a biology that almost didn't happen, from the evolutionary path that almost took a different turn at a dozen separate junctions, from a mind that, by every honest statistical reckoning, should not exist, and which finds itself, against all probability, in possession of exactly enough knowledge to understand the weight of what it almost didn't become. The numbers that describe that path, the probabilities stacked against each transition in the chain from simple chemistry to complex civilization, are what we need to examine next, because the silence of the sky is not merely a philosophical observation. It is a mathematical statement. And when you work out the mathematics carefully, with the data we actually have rather than the data we wish we had, the statement it makes is one of the most isolating conclusions in the history of human thought. I've read the full document carefully. Now I'll write Part 4 to seamlessly continue from where Part 3 ends, matching the voice, rhythm, and philosophical depth precisely. There is a particular kind of stillness that exists only at the edges of things. At the edge of a continent, where the land simply stops and the water begins and the horizon offers nothing but the flat gray certainty of distance. At the edge of a forest at night, where the last light falls between the trees and beyond is a darkness that has no floor. At the edge of the solar system, where the sun's influence fades to something barely distinguishable from the background radiation of the cosmos, and the nearest other star is so far away that the fastest spacecraft humanity has ever launched will require 70,000 years to reach it. These are not merely physical edges. They are the places where the mind encounters something that was not entirely designed to accommodate the raw, unmediated scale of the universe that was not built to human proportions, and which contains, as far as any instrument we can determine, no other minds like ours anywhere within reach. But the silence of the outer solar system, pressing in from all directions at light-hour distances, is not the only silence that matters. There is a closer silence, more immediate, more operational, and in some ways more dangerous than the void between stars. It is the silence of a solar system that humanity is beginning to fill, slowly, tentatively, with probes and telescopes and the first drawings of architecture that does not yet exist, and which contains, distributed across its geometry, enough kinetic energy, enough strategic asymmetry, enough legal and communicative vacuum to make the competition for its resources one of the most dangerous transitions in the history of the species. We have already traced the geometry of that danger. The asteroid belt with its billion tons of mobile kinetic energy, the Lagrange points with their permanent gravitational anchors and their legal emptiness, the moons of Jupiter immersed in radiation belts lethal to unshielded biology, the communication delays that sever any coherent chain of command the moment a human installation crosses the orbit of Mars. But there is one dimension of that danger we have not yet followed to its conclusion, one consequence of conflict in this environment that has no precedent in the history of warfare on Earth, and which represents perhaps the most chilling strategic reality of any war fought beyond the atmosphere. In 1978, the NASA scientist Donald Kessler published a paper describing a collision cascade he called, in the understated language of scientific literature, orbital debris flux. The scenario is simple in its mechanics and catastrophic in its consequences. Two objects collide in orbit. Each generates fragments. Those fragments, traveling at orbital velocities of several kilometers per second relative to the Earth's surface, proceed to collide with other objects. Those collisions generate more fragments. The fragments multiply geometrically, filling the orbital shell with a shrapnel field dense enough that any new object entering it, any satellite, any spacecraft, any inhabited station, is struck almost immediately. The orbital zone does not empty over time. It fills. Each collision feeds the next. The cascade accelerates until the altitude band is so saturated with debris that it becomes, for all practical purposes, permanently inaccessible. For centuries, perhaps longer, the shell of orbital space at that altitude is sealed, not by force, not by law, but by the mathematics of collision probability and the inescapable fact that no object moving through dense shrapnel at 7 kilometers per second can be expected to survive. This is what Kessler described for low Earth orbit, and it is a problem we have been gently approaching for decades, adding to the orbital population with every launch and every satellite and every rocket stage left adrift. But the Kessler cascade as a weapon, as a deliberate act of denial rather than an accidental consequence of carelessness, scales to something qualitatively different in the wider solar system. And when you extend the logic from a single orbital shell around Earth to the entire economic geography of a spacefaring civilization, the implications are not merely tactical. They are civilizational. Imagine the asteroid belt as it will exist a century or two from now. In any scenario where humanity has extended its economic reach beyond Earth's orbit, not the dense rock field of science fiction. We have already dismissed that fantasy, but the actual belt, sparsely populated, with mining installations on selected asteroids, mass drivers accelerating process or toward the inner system, communications networks linking the installations to each other and Earth and Mars, fuel depots positioned at key orbital locations to enable the transit of cargo and personnel across the belt's enormous volume. This is not an extravagant projection. It is a logical extension of economic pressures already visible in Earth's resource markets and in the engineering proposals already circulating in the aerospace industry. The asteroid belt is estimated to contain mineral resources with nominal economic value, if extracted and delivered to Earth vicinity, measured in the quintillions of dollars, a number so large it stops functioning as an economic quantity and starts functioning as a description of civilization-scale material abundance. Now introduce conflict, not the slow, deliberate kind, the kind that might be negotiated, mediated, resolved through the legal frameworks that humanity has built imperfectly and incompletely over centuries of painful experience. Introduce the fast kind, the kind driven by scarcity and fear and the logic of preemption, the conviction that if you do not act first, your adversary will, and the asymmetry of the first strike is too great to accept. In a solar system where a nudged asteroid carries kinetic energy equivalent to thousands of nuclear warheads, where mass drivers are industrially identical to bombardment systems, where communication delays mean that authorization from a home authority will arrive only after the engagement has already concluded. In this environment, the logic of preemption is not irrational. It is a rational conclusion of actors who understand the geometry of their situation and who have no reliable mechanism for credible commitment. A conflict in the asteroid belt does not end cleanly. It cannot, because the weapons available in that environment, the nudged rocks, the accelerated slugs, the diverted or shipments repurposed into kinetic impactors, do not expire. They do not rust. They do not lose velocity or direction in the vacuum of interplanetary space, where there is no atmosphere to create drag and no medium to absorb their momentum. An iron slug launched from a mass driver in the belt, aimed at a trajectory that will carry it toward the inner solar system, continues on that trajectory indefinitely. If it misses its intended target, or if its intended target is a mining facility that is destroyed before the slug arrives, the slug continues. It does not know the war is over. It does not know anything. It is a mass moving through a vacuum at a fixed velocity in a fixed direction, subject only to the slow gravitational influences of the planets it passes near, which may alter its trajectory over centuries in ways that are difficult to predict precisely. A war fought in the asteroid belt today does not end when the last combatant stands down. It creates a population of dormant projectiles scattered across the inner solar system, iron slugs, diverted asteroids, fragments of destroyed installations, traveling silently through the darkness on trajectories that may not intersect with any inhabited body for decades or centuries or millions of years. The solar system, after such a conflict, is a minefield, not a minefield that can be swept, not a minefield that degrades over time, a permanent minefield, a population of unpowered, silent, undetectable impactors distributed through a volume of space so vast that cataloging all of them would require more observational capacity than any civilization has yet possessed. Whatever intelligence inherits this solar system after us, whether it's our own descendants or something else that finds the address vacant and moves in, inherits the ordnance we left behind. A war we fought and perhaps settled or forgot persists in the darkness for geological time. This is not a speculative horror. It is a physical consequence of kinetic warfare in a vacuum. The only scenario in which it does not occur is the one in which no such warfare takes place. And the question of whether that scenario is achievable, whether the competitive pressures, the legal vacuums, the communication delays, and the strategic asymmetries of a multi-planetary civilization can be managed peacefully, is not a physics question. It is a governance question, a psychology question, a question about whether a species that has spent most of its history failing to coordinate adequately for its own survival can learn to do so at a scale and in an environment that punishes failure with consequences that last longer than recorded history. The permanence of the solar system scale Kessler cascade, an instigation of cascading debris across entire economic zones, rendering the orbits of Jupiter's moons or the processing lanes of the belt inaccessible not for years, but for centuries, means that the winner of such a conflict does not win the solar system. The winner inherits a lock cage. They win control over a volume of space, so contaminated with the residue of their own victory, that the resources they fought for may be unreachable for generations. The asteroid belts or does not disappear into a debris cascade. It becomes inaccessible. The Lagrange points retain their gravitational stability, but become surrounded by shrapnel fields that any new installation must somehow survive. The infrastructure that made the outer solar system economically valuable is the first casualty of any serious effort to deny it to an adversary. Scorched Earth, taken to its logical extreme in an environment where the Earth is replaced by an entire economic zone's worth of orbital geometry. A civilization that begins a resource war in the outer solar system risks ending it in possession of ruins, so thoroughly ruined that rebuilding takes longer than the original development. This is a physical argument against space warfare, and it is a compelling one. But the more interesting argument, the one that operates not from the physics of debris dynamics, but from the psychology of sheer mortality, is the argument from the environment itself. Because the outer solar system does not merely make warfare costly, it makes it, in a very specific and deeply structural sense, collectively suicidal in a way that no war on the surface of a planet has ever quite managed. Consider what every human installation in the outer solar system has in common, regardless of which nation or corporation or political faction operates it. Every one of them depends on sealed environments. Every one of them depends on the integrity of systems, life support, power generation, pressure maintenance, radiation shielding, whose failure is not a setback, but an extinction event for everyone inside. The margin between a functioning habitat and a coffin, in the outer solar system, is measured in centimeters of home material and fractions an atmosphere of pressure differential. There is no improvisation available. There is no retreating to safer position, no foraging for resources, no surviving off the land while the infrastructure is rebuilt. In the outer solar system, the infrastructure is a survival, and anything that compromises the infrastructure kills everyone it was protecting with a speed and certainty that has no parallel in any terrestrial conflict scenario. This shared dependence on sealed systems creates something that political theorists have rarely had the opportunity to observe in pure form. A situation in which the interests of the individual actors, their survival, are entirely aligned with the integrity of the shared environment and entirely destroyed by its violation. On Earth, a nation can bomb an adversary's infrastructure and survive on its own. In a Europan subsurface habitat, a faction that destroys the opposing faction's life support systems may find itself sealed in a facility with a compromised atmospheric recycling loop, no longer able to call for help from their own automated supply nodes, isolated by the unforgiving geometry of the Jovian system itself at the speed of light, and months away at the speed of any physical vehicle. The analogy that comes closest is the Antarctic Treaty, not as a model of idealistic international cooperation, but as a model of cooperation enforced by physics. Antarctica is governed by a treaty signed in 1959 that has, by the standards of international agreements, been remarkably stable. No military installations, no territorial claims, Scientific research conducted cooperatively across national boundaries that, on any other continent, will be defended with warships. The reason the Antarctic Treaty works is not primarily that nations are more noble in Antarctica than elsewhere. It is that Antarctica is an environment that kills the uncooperative. A research station that antagonizes its neighbors cannot easily replace the spare parts, the medical support, the search and rescue capability, the logistical chain that keeps it alive through an Antarctic winter. The hostility of the environment enforces a minimum of cooperation that no amount of political goodwill alone has been able to maintain in more forgiving landscapes. The outer solar system is Antarctica scaled by every order of magnitude the solar system can provide. The environmental hostility is not a deterrent to conflict among humans. It is a constant structural pressure toward cooperation, not out of sentiment, not out of legal obligation, but out of the simple recognition that in this environment, your adversary's life support system is your safety margin. A culture that learns to recognize this does not become peaceful because it is virtuous. It becomes peaceful because the alternative is a solar system full of expanding clouds of debris and sealed habitats full of corpses, and the mathematics of that outcome are not difficult to calculate. The question of whether cooperative logic wins over competitive one, whether the Antarctic model scales to the asteroid belt in the Jovian system, or whether the resource pressures and the legal vacuums and the communication delays fracture any cooperative framework before it can solidify, is not answerable by the data we currently possess. It is a question about the future, and the future is not yet written. But the physical environment has already cast its vote. The solar system is not set up to reward warfare. It is set up to punish it with consequences that persist for geological time. Whether humanity chooses to receive that message before or after it has already written the punishment into the permanent landscape of the inner solar system is, at this moment, genuinely open. And it is genuinely open in a way that it would not be if the backward-facing interpretation of the Great Filter were false. If the universe were full of civilizations, if the optimistic reading of the Drake equation were correct, and intelligence arose wherever the chemistry allowed, and there were thousands or millions of technological species distributed across the Milky Way, then the question of our survival will be nested inside a much larger statistical picture. We would be one data point among many, and whatever we did or failed to do would be one outcome among a large sample. The universe, in that scenario, would be conducting an experiment with many runs, and our particular run would matter in a human sense, enormously, personally, cosmically. But it would not be the only run. There would be others. The backward-facing filter changes this entirely. And the change is not primarily intellectual. It is emotional. It is a shift in the quality of the stakes. A shift so profound that it is difficult to find an analogy for it in ordinary human experience. Because ordinary human experience has never had to accommodate the possibility that you are literally the only one. Most people encounter the Fermi Paradox as a fascinating puzzle, a topic for late-night conversation, a source of that particular pleasurable anxiety that comes from contemplating scales too large to fully internalize. This is a forward filter framing of the paradox. It is a warning about what might happen to us, and warnings, however dire, are still about a possible future that has not yet arrived. The backward-facing filter is not a warning. It is a description of what has already happened, not to us, to everyone else. Every other experiment in the universe ran in the direction of complexity, and consciousness either never started or stopped somewhere along a path that leads, on this one world, all the way to a mind capable of calculating the odds of its own existence. The weight of that is not primarily philosophical, though it is that too. It is moral. If the universe has produced exactly one experiment in mind, one node of organized consciousness in 13.8 billion years of cosmic history, on one world orbiting one star in one unremarkable corner of one galaxy among 2 trillion, then that mind is not merely interesting. It is the only custodian the universe has ever produced of its own inner life. Every piece of music ever written, every mathematical proof ever constructed, every moment of grief and every moment of wonder, and every abstract question asked late at night about the nature of existence, All of it is housed in the only structure of organized self-awareness the cosmos has managed to produce in nearly 14 billion years of trying. This is not mysticism. It is a straightforward consequence of the data. If the data supports the backward-facing filter, and the consequence is not a comfortable one to live inside, it reframes every human conflict, every war for territory, every competition for resources, every ideological fracture that divides one portion of the species from another, not merely as a tragedy in the ordinary sense, but as something closer to desecration. When the canvas is singular, damage to the painting is not recoverable from elsewhere. There is no elsewhere. There is only here. There is only now. There is only this narrow window of biological possibility, maintained by the continued functioning of a civilization that is the sole custodian of the only consciousness the universe has managed to produce. The forward filter made the argument for human survival urgent. It said, "Be careful. Something ahead may kill you. History suggests civilizations fail, and we do not want to be one of them." The backward filter makes the argument for human survival absolute. It does not say, "Be careful, you might be destroyed." It says, "Understand what you are. You are not one species among many. You are not one experiment the universe runs among a population of thousands. You are the universe's one successful experiment in turning matter into a mind. Your extinction is not the loss of one species. It is the erasure of the only reflective surface the cosmos has found in all its 14 billion years, the only place where the universe can, even briefly, look at itself. There is no external authority that can explain this to us. No older civilization to put in context, because if the backward-facing filter is correct, there is no older civilization, no interstellar community to welcome us when we achieve sufficient sophistication, because the sophistication we have achieved is already, by all available evidence, the maximum that has ever existed anywhere. We are not the young species looking up at the galaxy and wondering where the elders are. We are the elders. We are the oldest intelligence the galaxy has ever produced, and we are doing what young species do, fighting over the surface of the single world that made us, approaching the boundaries of the single solar system that contained us, with the tools and the awareness and the improbability that billions of years of cosmic contingency assembled specifically and exclusively for us, and doing all of this without fully understanding what we are. The understanding, when it comes, tends to arrive quietly, not in the moment of urgency and noise that fill the daily record of human activity, but in the other kind of moment, the kind that exists at the edge of sleep, or at the edge of a continent, or at the edge of whatever vocabulary remains after the science has been followed to its conclusion, and what is left is not an equation but a feeling. The feeling of looking up at a dark sky and knowing that the darkness is not merely vast. It is empty in a way that is specific to this moment in the universe's history, and perhaps to this location in it, and that whatever fills it, whatever mind eventually spreads through those enormous cold distances and makes them into a home, will be continuous with whatever is reading these words or hearing this voice right now. There is a version of human history in which the silence of the cosmos is an instruction, not a warning, not a threat, not a description of failure, an instruction. It says, "You are what you appear to be. You are the first attempt. You are the thing the universe built after 13.8 billion years of rehearsal, and you are not finished being built. The transition from a single world species to a multi-world species, from a species that fights over the surface of one planet to a species that learns to govern itself across the enormous, hostile, legally empty distances of the solar system. That transition is not merely political or technological. It is developmental. It is the next stage of the same journey that began in the chemistry of ancient oceans and continued through every extinction and every near miss and every improbable contingency that the planetary record has preserved. And every step of that journey, when you trace it carefully, shows the same pattern. Not triumph, not the inevitable ascent of complexity toward consciousness as a destination, but survival, narrow, improbable, contingent survival, each moment purchased by a combination of favorable physics and fortunate timing that the universe has not repeated anywhere else we can detect. The eukaryotic cell arose once. Complex multicellular animals arose once. The Cambrian explosion, for all its proliferation of body plans, was a single event on a single world. Language arose once. The scientific method arose once. The realization that the stars are other suns, that the universe has a history, that the silence of the sky is a message rather than merely a background. These arose once, in the minds of one species, on one world that was already ancient by the time the first of those minds looked up and began to measure. We are not at the beginning of this story. We are deep inside it. The beginning was billions of years ago, in chemistry and geology, and the slow accumulation of complexity in an ocean that no living thing had yet named. What we are at is an inflection point, the moment when the species that the story produced becomes aware enough of the story to understand its own position in it, aware enough to read the silence correctly, aware enough to understand that the silence is not merely absence, but information, the most important information the universe has offered us, which is that the universe does not make minds easily, and that the mind it managed to make here on this world at this moment in cosmic time carries a weight that is as literal as it is figurative, the weight of being first. Not the first in a sequence that will eventually catch up, not the pioneer who is followed, decades later, by settlers who make the journey ordinary, the first in the sense of singular, the first in the sense that nothing in the 13.8 billion years before this moment produced anything capable of asking the question that this moment demands. What do we do now, knowing what we know? The answer is not written anywhere. It has never been written anywhere, because there has never been anyone to write it. The position we occupy has no precedent. The responsibility we carry has no analogy in any political or philosophical tradition built for a species that believed, even unconsciously, that it existed among others of its kind. We build our ethics for a world in which there were neighbors. We are only now beginning to suspect that there are none, that the neighborhood extends in every direction to the edge of the observable universe, and that every address in it is empty, and that the single occupied house in all that enormous, indifferent darkness is the one we are standing in. Let that rest for a moment. Let the scale of it settle without filling it immediately with response or resolution. This is what the science has assembled, piece by piece, from geology and astrophysics and molecular biology and planetary science, and 60 years of listening to a sky that has said nothing in return. The great filter is not in front of us. It is behind us. We pass through it bleeding and improbably in over enormous spans of time that we can measure but cannot fully feel. And we arrived here, at this world, at this moment, at this particular arrangement of matter capable of looking at itself with something like understanding. The sky outside is dark now. Whatever time it is where you are, whatever city or countryside or empty road you find yourself in, the same darkness extends outward from every horizon in every direction, through the thin skin of the atmosphere, and past the slowly drifting debris of the orbits we have begun to fill, and out to the solar system's enormous quiet distances, past Jupiter's radiation belts and Saturn's geometric rings, and the long cold dark beyond the outer planets, and then further still, through the interstellar medium and the structure of the local group and the vast, bubble-pocked architecture of the cosmic web. And nowhere in all that immensity, as best we can determine with every instrument we have built, is there another voice. That silence is not abandonment. It is not evidence of a universe indifferent to life, in the sense of being opposed to it. The universe is not opposed to anything. It does not have preferences. It has physics, and the physics, over 14 billion years, produce one outcome complex enough to notice. One world, one sky, one species at the edge of understanding what it is. The first light of morning will come regardless of what we decide. The Earth will continue its orbit, patient and indifferent in the way that planets are, carrying its cargo of improbable biology around a star that does not know it is special. The oceans will move. The atmosphere will circulate. The biosphere will do what it has done for 4 billion years. Adapt, compete, persist, maintain the slow chemical negotiation with entropy that is the definition of life. But somewhere on the surface of that world, a mind will wake up, It will look at the sky before the day fills it with noise and urgency and all the machinery of ordinary human time. And if it knows what to look for, if it carries the knowledge of what the silence means and what the improbability means and what the way to be in the first truly complex mind in the observable universe means, it will feel, before the thoughts come in, and organize the feeling into language, something that is not quite awe and not quite grief and not quite responsibility, but is all three of those things simultaneously and more. It will feel the weight of the one, the singular, improbable, unchaperoned fact of being here, not as a species among millions of species on a world among millions of worlds hosting intelligence, but as the one, the experiment that worked, the thread that did not break, the thing the universe tried to make across billions of years and trillions of worlds and manage here once. A young species, still learning the names of things, still learning to share the surface of the world that made it, still making the mistakes that young things make, loud and urgent and sometimes destructive, with all the graceless momentum of anything that is still in the process of becoming what it will eventually be. But here, awake, looking up, and the darkness above is patient. It has been waiting in its indifferent way for 14 billion years. It can wait a little longer, while this one small, improbable, magnificent mind finishes the long and difficult work of learning who it is, and whether it can manage to share a sky before it tries to claim the stars.